welcome to the stage NVIDIA founder and CEO, Jensen Huang.
Welcome to GTC! What an amazing year. We wanted to do this at NVIDIA. So through the magic of artificial intelligence, we're going to bring you to NVIDIA's headquarters. I think I'm bringing you to NVIDIA's headquarters. What do you think? This is where we work. This is where we work. What an amazing year it was, and we have a lot of incredible things to talk about. And I just want you to know that I'm up here without a net. There are no scripts, there's no teleprompter, and I've got a lot of things to cover, so let's get started. GTC started with GeForce. It all started with GeForce. And today, I have here a GeForce 5090, and 5090, unbelievably, 25 years later, 25 years after we started working on GeForce, GeForce is sold out all over the world. This is the 5090, the Blackwell generation, and comparing it to the 4090, look how it's 30% smaller in volume. It's 30% better at dissipating energy and incredible performance. Hard to even compare, and the reason for that is because of artificial intelligence. Just has to do with all of the other industries that I've demonstrated. And so today, I'm super excited to announce that GM has selected NVIDIA to partner with them to build their future self-driving car fleet. The time for autonomous vehicles has arrived, and we're looking forward to building with GM AI in all three areas. AI for manufacturing, so they can revolutionize the way they manufacture. AI for enterprise, so they can revolutionize the way they work, design cars and simulate cars, and then also AI for in the car. So AI infrastructure for GM, partnering with GM and building with GM their AI. So I'm super excited about that. One of the areas that I'm deeply proud of, and it rarely gets any attention, is safety, automotive safety. It's called halos. In our company, it's called halos. Safety requires technology from silicon to systems, the system software, the algorithms, the methodologies, everything from diversity to ensuring diversity, monitoring and transparency, explainability. All of these different philosophies have to be deeply ingrained into every single part of how you develop the system and the software. We're the first company in the world, I believe, to have every line of code safety assessed. 7 million lines of code safety assessed. Our chip, our system software, and our algorithms are safety assessed by third parties that crawl through every line of code to ensure that it is designed to ensure diversity, transparency, and explainability. We also have filed over 1,000 patents, and during this GTC, and I really encourage you to do so, is to go spend time in the Halos workshop so that you could see all of the different things that comes together to ensure that cars of the future are going to be safe as well as autonomous. And so this is something I'm very proud of. It rarely gets any attention, and so I thought I would spend the extra time this time to talk about that. Okay, NVIDIA Halos. Incredible. Artificial intelligence has made extraordinary progress. It has only been 10 years. Now, we've been talking about AI for a little longer than that. But AI really came into the world's consciousness about a decade ago. Started with perception AI, computer vision, speech recognition, then generative AI. The last 5 years, we've largely focused on generative AI, teaching an AI how to translate from one modality to another modality, text to image, image to text to video, amino acids to proteins, properties to chemicals, all kinds of different ways that we can use AI to generate content. Generative AI fundamentally changed how computing is done. From a retrieval computing model, we now have a generative computing model. Whereas almost everything that we did in the past was about creating content in advance, storing multiple versions of it, and fetching whatever version we think is appropriate at the moment of use. Now, AI understands the context, understands what we're asking, understands the meaning of our request, and generates what it knows. If it needs, it'll retrieve information, augments its understanding, and generate answer for us. Rather than retrieving data, it now generates answers. Fundamentally changed how computing is done. Every single layer of computing has been transformed. The last several years, the last couple, 2-3 years, major breakthrough happened. Fundamental advance in artificial intelligence. We call it agentic AI. Agentic AI basically means that you have an AI that has agency. It can perceive and understand the context of the circumstance. It can reason, very importantly, it can reason about how to answer or how to solve a problem, and it can plan in action. It can plan and take action. It can use tools because it now understands multimodality information. It can go to a website and look at the format of the website, words and videos, maybe even play a video. Learns from what it learns from that website, understands it, and come back and use that information, use that newfound knowledge to do its job. Agentic AI. At the foundation of agentic AI, of course, something that's very new, reasoning. And then, of course, the next wave is already happening. We're going to talk a lot about that today. Robotics, which has been enabled by physical AI. AI that understands the physical world. It understands things like friction and inertia, cause and effect, object permanence. When something goes around the corner, it doesn't mean it has disappeared from this universe. It's still there, just not seeable. And so that ability to understand the physical world, the three-dimensional world, is what's going to enable a new era of AI we call physical AI, and it's going to enable robotics. And this year, we're going to talk a lot about agentic AI and physical AI. At its core, what enables each wave and each phase of AI, three fundamental matters are involved. The first is how do you solve the data problem? And the reason why that's important is because AI is a data-driven computer science approach. It needs data to learn from. It needs digital experience to learn from, to gain to learn knowledge and to gain digital experience. How do you solve the data problem? The second is how do you solve the training problem without human in the loop? The reason why human in the loop is fundamentally challenging is because we only have so much time, and we would like an AI to be able to learn at superhuman rates, at super real-time rates, and to be able to learn at a scale that no humans can keep up with. And so the second question is, how do you train the model? And the third is, how do you scale? How do you find an algorithm whereby the more resource you provide, whatever the resource is, the smarter the AI becomes? The scaling law. Well, this last year, this is where almost the entire world got it wrong. The computation requirement, the scaling law of AI is more resilient and, in fact, hyper-accelerated. The amount of computation we need At this point, as a result of agentic AI, as a result of reasoning, is easily 100 times more than we thought we needed this time last year. From the old way of doing data centers to a new way of building these infrastructure, and I call them AI factories. They're AI factories because it has one job and one job only, generating these incredible tokens that we then reconstitute into music, into words, into videos, into research, into chemicals or proteins. We reconstitute it into all kinds of information of different types. So the world is going through a transition in not just the amount of data centers that will be built, but also how it's built. To take you to a digital twin we call NVIDIA. All right, let's talk about data centers. That's not bad, huh? Gaussian splats, just in case. Gaussian splats. Well, let's talk about data centers. Blackwell is in full production, and this is what it looks like. It's an incredible, you know, for people, for us, this is a sight of beauty. Would you agree? This is, how is this not beautiful? How is this not beautiful? Well, this is a big deal because we made a fundamental transition in computer architecture. We were trying to solve scale up. Distributed computing is about using a whole lot of different computers working together to solve a very large problem. But there's no replacement for scaling up before you scale out. Both are important, but you want to scale up first before you scale out. Well, scaling up is incredibly hard. There is no simple answer for it. You're not going to scale it up, you're not going to scale it out like Hadoop. The problem we're trying to solve is so complex that scaling in that way would have simply cost way too much power, way too much energy. It would have never, deep learning would have never happened. And so the thing that we had to do was scale up first. This is equivalent to these two things in compute. What's amazing is this is completely liquid cooled, and by liquid cooling it, we can compress all of these compute nodes into one rack. This is the big change of the entire industry. All of you in the audience, I know how many of you are here. I want to thank you for making this fundamental shift from integrated NVLink to disaggregated NVLink, from air-cooled to liquid-cooled, from 60,000 components per computer or so to 600,000 components per rack, 120 kilowatts, fully liquid cooled, and as a result, we have a 1 exaflops computer in one rack. Isn't it incredible? Okay. As all of you know, if you have a wedding party of 300 and you're trying to find the perfect, well, the optimal seating for everyone, that's a problem that only AI can solve or a mother-in-law can solve. And so that's one of those problems that co-op cannot solve. Okay, so what you see here is that we gave it a problem that requires reasoning, and you saw R1 goes off and it reasons about it, tries all these different scenarios, and it comes back and it tests its own answer. It asks itself whether it did it right. Meanwhile, the last generation language model does a one-shot. So the one-shot is 439 tokens. It was fast, it was effective, but it was wrong. So it was 439 wasted tokens. On the other hand, in order for you to reason about this problem, and this is just that was actually a very simple problem. We just give it a few more difficult variables, and it becomes very difficult to reason through. And it took 8,000, almost 9,000 tokens. And it took a lot more computation because the model's more complex. And so the software, the operating system for these AI factories is insanely complicated. That piece of software is insanely complicated. And so today we're announcing the NVIDIA Dynamo. Now we call it Dynamo for a good reason. As you know, the Dynamo was the first instrument that started the last industrial revolution, the industrial revolution of energy. Water comes in, electricity comes out. It's pretty fantastic. Water comes in, you light it on fire, turn to steam, and what comes out, this is an invisible thing that's incredibly valuable. It took another 80 years to go to alternately current, but Dynamo is where it all started. Okay, so we decided to call this operating system, this piece of software, insanely complicated software, the NVIDIA Dynamo. It's open source, and we're so happy that so many of our partners are working with us on it. And one of my favorite partners, I just love them so much because of the revolutionary work that they do, and also because Aravin's such a great guy, but Perplexity is a great partner of ours in working through this. Okay, so anyhow, really, really great. That 1 megawatt data center. And so that's your goal. On the one hand, you would like your token rate to be as fast as possible so that you can make really smart AIs. And if you have smart AIs, people pay you more money for it. On the other hand, the smarter the AI, the less you can make in volume. Very sensible trade-off. And this is the curve we're trying to bend. Now, what I'm just showing you right now is the fastest computer in the world, Hopper. It's the computer that revolutionized everything. And so how do we make that better? So the first thing that we do is we come up with Blackwell with NVLink 8. Same Blackwell, that one same compute, and that one compute node with NVLink 8 using FP8. And so Blackwell is just faster, bigger, more transistors, more everything. But we like to do more than that, and so we introduce a new precision. It's not quite as simple as 4-bit floating point, but using 4-bit floating point, we can quantize the model, use less energy to do the same. And as a result, when you use less energy to do the same, you could do more. Then we scale up with NVLink 72. Does that make sense? Look at the difference between that NVLink 72 FP4, and then, because our architecture is so tightly integrated, and now we add Dynamo to it, Dynamo can extend that even further. Are you following me? So Dynamo also helps Hopper, but Dynamo helps Blackwell incredibly. Now, yep. Only at GTC do you get an applause for that. And so now notice what I put, those two shiny parts, that's likely where you'll run your factory operations. You're trying to find that balance between maximum throughput and maximum quality of AI. Smartest AI, the most of it. Those two, that XY intercept is really what you're optimizing for. And that's what it looks like if you look underneath those two squares. Blackwell is way, way better than Hopper. Now here's that rainbow. That's incredible. That's the fun part. This image says very, very clearly you want a programmable architecture that is as homogeneously fungible as possible, because the workload changes so dramatically across the entire frontier. The configuration of the computer is changing across that entire spectrum. And then this is what happens. So this is with input sequence length. This is a kind of a commodity test case. This is a test case that you can benchmark relatively easily. The input is 1,000 tokens. The output is 2,000. Notice earlier, we just showed you a demo where the output is very simply 9,000, right? 8,000, okay? And so obviously this is not representative of just that one chat. Now this one is more representative, and this is what the goal is to build these next generation computers for next generation workloads. And so here's an example of a reasoning model. And in a reasoning model, Blackwell is 40 times the performance of Hopper. Straight up. Pretty amazing. And all the other slides took 30 minutes. All right, so next, let's go somewhere else. Let's go talk about robotics, shall we? Let's talk about robots. Well, the time has come. The time has come for robots. Robots have the benefit of being able to interact with the physical world and do things that otherwise digital information cannot. We know very clearly that the world has severe shortage of human laborers, human workers. By the end of this decade, the world is going to be at least 50 million workers short. We'd be more than delighted to pay them each $50,000 to come to work. We're probably going to have to pay robots $50,000 a year to come to work. And so this is going to be a very, very large industry. There are all kinds of robotic systems. Your infrastructure will be robotic. Billions of cameras in warehouses and factories, 10, 20 million factories around the world. Every car is already a robot, as I mentioned earlier, and then now we're building general robots. A framework that is used by roboticists all over the world with Joko. And so today we're announcing something really, really special. It is a partnership of 3 companies, DeepMind, Disney Research, and NVIDIA, and we call it Newton. Let's take a look at Newton. Tell me that wasn't amazing. Hey, Blue. How are you doing? How do you like your new physics engine? You like it, huh? Yeah, I bet. I know. Tactile feedback, rigid body, soft body simulation, super real time. Can you imagine just now what you were looking at is complete real-time simulation? This is how we're going to train robots in the future. Just so you know, Blue has 2 computers, 2 NVIDIA computers inside. Look how smart you are. Yes, you're smart. Okay. All right. Hey, Blue, listen. How about let's take them home? Let's finish this keynote. It's lunchtime. Are you ready? Let's finish it up. We have another announcement. You're good. You're good. Just stand right here. Stand right here. Stand right here. All right, good. Right there. That's good. All right, stand. We have one more treat for you. Play it. Thank you, everybody. Thank you for all the partners that made this video possible. Thank you, everybody that made this video possible. Have a great GTC. Thank you. Hey, Blue. Let's go home. Good job.